Okay, continuing here, we're going to talk about the graphs of polynomial functions. Now there's a lot of content about polynomial functions, so we're going to take it one step at a time. The definition of a polynomial function, you can give a polynomial function using coefficients like a to the n, a to the n minus 1, a2, a1, a0, where basically a to the n is the coefficient of whatever term is to the nth power, and then a sub n minus 1 is the coefficient of the x to the n minus 1 term, and then a2 is the coefficient of x squared term, a1 is the coefficient of the x term, and a sub 0 is the constant term. And so the degree is, of course, the highest degree or the highest power of x here. So this would be an n degree polynomial. And a sub n would be the leading coefficient. So here are some examples of polynomials, and I've written them in descending order. Here's a polynomial of degree 2 where the leading coefficient is square root of 5. Here's a polynomial of degree 10 where the leading coefficient is actually 5. And here's a polynomial of degree 4 where the leading coefficient is 1. Now what's interesting about polynomial functions of degree 2 or higher, now remember degree 1 would be linear functions, but of degree 2 or higher, they all have graphs that are smooth and continuous. In other words, the curves are rounded, they have no breaks or sharp corners. So the first test we're going to look at is we're going to look at the leading coefficient test. As x increases or decreases without bound, the graph of the polynomial function given by this eventually rises or falls. So eventually the graph will rise or fall, but let's see when it rises or falls. If n is odd, so let's say the leading term has an odd exponent like these two down here. Both of these have a leading exponent of 3. So there's two possibilities. If the degree is an odd number, if the degree is odd, if the leading coefficient is positive, then the graph falls to the left and rises to the right. So here the leading coefficient is 2, and notice that if you go to the left the graph falls, but as you move to the right the graph rises. Now same degree, odd degree, but the leading coefficient is negative, then it does just the opposite. As you go to the left the graph will eventually rise, and as you go to the right the graph will eventually fall. Now if you have an even exponent, if n is even, like here both of these have degree 4 here and here, if the leading coefficient is positive the graph rises to the left and rises to the right. So it rises on both sides if the coefficient is positive. So it rises on the left and it eventually rises on the right. Now if it's negative, it's actually going to fall to it's eventually going to fall to the left and it's going to fall to the right. Okay, so that's how the leading coefficient test works. And so you can freeze the video and read these examples I've given you here, but you should be able to figure it out pretty easily. Here you have an even, exponent is even, so even would put us over here, and if the coefficient is positive, which is what we have here, 7 is positive, then the graph rises to the left and rises to the right. But then when you move down here, the graph is odd, and the coefficient is understood to be 1, so the lead coefficient is positive, so the graph falls to the left and rises to the right, like it did up here with this one. Okay, and you can read the other two. Okay, so now let's talk about zeros of polynomial functions in multiplicity. So let's say you wanted to find the zeros. Now when we say find the zeros, we mean we set the polynomial equal to 0 and solve it. Well, this one can be solved by, if you do factor by grouping. I can factor an x squared out of the first two terms, and I can factor a negative 1 out of these two terms, and then when I factor the x plus 3 out of here and here, I get x squared minus 1, which eventually factors into x plus 1, x minus 1. So I can solve this by factoring, and determine that what makes x plus 3 equals 0 is negative 3, and then x plus 1 would give me negative 1, x minus 1 would give me a root of 1. Over here I can factor, set this equal to 0, I can factor negative x squared out, and I get x squared minus 4x plus 4. Well, for negative x squared, for this to be 0, x squared would have to be 0, or this trinomial has to be 0. Well, the only way x squared can be 0 is x is 0, but this trinomial factors into x minus 2 quantity squared, so the only way that can be 0 is that if x equals 2. Now, if you'll notice over here, each root occurred once. Okay, negative 3, negative 1, 1. But technically over here, the root 2 occurs twice, because if you think about this factor, it's x minus 2 times x minus 2. So one could say that the 2 occurs as a root twice. Well, that has to do with multiplicity. The multiplicity of a 0 is the number of times that the corresponding factor occurs. For example, if you had a polynomial like this, it would have 3 roots, or 3 zeros, 0, 1, and negative 3. Well, 0, since this is squared, 0 would be a multiplicity of 2, and for 1 you would get a multiplicity of 1, but for negative 3 you would get a multiplicity of 3, since the factor occurs 3 times. So if you go back to the examples I just had, that one, this one, actually I didn't mention this a minute ago, but 0 has a multiplicity of 2 as well. So 0 has a multiplicity of 2, and 2 has a multiplicity of 2. Now over here, this factor, negative 1, x plus 1 occurs once, so negative 1 is a 0 with multiplicity of 1, but this factor occurs 3 times because it's cubed, so if you solve that, you would get 3 halves as a 0, and it would have a multiplicity of 3. Now, let's talk about multiplicity and the x-intercept. So let's say a root is a 0 of even multiplicity. In other words, it's multiplicity of 2 or 4. Then the graph touches the x-axis and turns around at that number. But if r is a 0 of odd multiplicity, so maybe the factors only to the first power or the third power, then the graph crosses the x-axis at r. So even multiplicity, it touches the x-axis and turns around. Odd multiplicity, it crosses the x-axis. So let's take a look at this graph. Okay, so we know that negative 1 has a multiplicity that's even, and 3 has a multiplicity that's odd. So negative 1 has even multiplicity, and so notice the graph just touches it at negative 1 and then turns around. Okay? But then x equals 3 has odd multiplicity. So notice the graph actually crosses the x-axis at 3. Okay? So basically that's how that works. Now, a theorem that's interesting is the intermediate value theorem. And it says let f be a polynomial function with real coefficients. If f of a and f of b have opposite signs, then there's at least one value c between a and b such that f of c is 0. In other words, f of x equals 0. Well, let's take a look at what we're talking about here. So let's say that you knew that at 2 that the graph was negative, and you knew that at 3 the graph was positive, so it'd be way up here somewhere. Okay, well, if that's the case for a polynomial function, then you know there's somewhere between 2 and 3 there's got to be a 0 or a root. Okay, so here's a function. Okay, so f of 2 is a negative number, negative 1, and f of 3 is a positive number, 16. So that tells me that this polynomial has to have at least one 0 between the numbers 2 and 3. Because otherwise, if a polynomial graph is smooth and continuous, then how can the graph go from this point that's below the x-axis up here somewhere above the x-axis without actually crossing the x-axis? So it has one real root. Now I actually used a computer program to figure it out. It's about 2.095, but that's just a decimal approximation. So here's another one. Show that x cubed minus 50 has at least one zero between 3 and 4. Well, f of 3, if you plug 3 in, you get a negative number. If you plug 4 in, you get a positive number. So by the intermediate value theorem, there has to be a number, at least one root of this function, between 3 and 4. Okay? So the cube root of 50, we already know if you actually calculate the cube root of 50, which is basically what that is, what the solution would be the cube root of 50, you'd find that it's a number between 3 and 4. Okay, freeze the video and then read this turning points and graphing strategy, and then when you think you've got it all figured out, start the video again and I'll show you how this works. Okay, so let's discuss the graph of this polynomial. Okay? Since this is a binomial squared, that'd be x squared, and then times this would give me x cubed. So I know the leading term has an odd exponent, and the leading term would be negative because of the negative 2. So since it's odd and negative, the graph must rise to the left and fall to the right. Now the x-intercepts, you can easily get the x-intercepts here to be 1, 0, and negative 2, 0. So you know down here that the graph crosses the x-axis there. But the 1, 0 has multiplicity 2, so it's just got to touch the graph and turn around, whereas the negative 2 has multiplicity 1, so it's going to cross the graph. So you can see down here it crosses the graph, and then at 1 it touches it and turns around. Okay, f of 0, you can find, if you plug 0 in for x, you can find the y-intercept. So the y-intercept is at 0, negative 4. Okay, now once I have that, and I know it's got to touch this and turn around, then I know it's got to just go up here and do a little turnaround from there. And the other thing is there's no symmetry, so it's not odd nor even, so there's no symmetry. And the maximum number of turning points, which is actually says that up here somewhere, is n minus 1. Remember, n was 3, third degree polynomial, so the maximum number of turning points is 2. And if you'll notice, the graph it turns twice. It turns here, right here, and then it turns right here. So that's the maximum number of turning points. So basically the idea is you can put all this together and get a graph using this information. And so the next one, I'll go through it real quick. This term, the exponent is even, and of course the coefficient is positive, so the graph rises to the left and rises to the right. The x-intercepts are 1, 0 and negative 1, 0, so you can plot those on the graph. Since if you go back and look at this, you get even multiplicity for both 1 and negative 1. So we know the graph touches the x-axis and turns at both of those. And f of 0 is 1, so we plot that. So basically, if I know these are the three intercepts, and I know the graph must come down and touch, so it's got to go down here and touch and turn around. And then also back here it's got to touch and turn around. So that pretty much kind of gives it away. The other thing, the maximum number of turning points, since the degree was 4, the maximum turning points is 3. And you can see there's one here at negative 1, 0, there's one here at 1, 0, and there's one here at 0, 1. So those are your 3 turning points. So that information is helpful in graphing polynomial functions. And we're going to add more information to this as we move through this chapter.